All right, so this week we're going to kind of take a little bit of a break from algebra and solving equations, and we're going to look at more graphing. Okay, we'll start out the week by looking at your basic trig functions, sine and cosine, which we saw earlier. Those are those nice waves. They're continuous. And then on Friday, we'll look at some of the other trig functions like tangent, cotangent, secant, and cosecant. We're going to go very in-depth with sine and cosine, okay, graphing all the transformations that you can. That's your horizontal shifts, your vertical shifts, and your horizontal stretching and compressing, and vertical stretching and compressing. When we get to tangent and secant, cosecant, cotangent, we're not going to go into as much depth with those functions because we don't use them as much. Okay, but we'll still look at them. All right, so the first thing about sine, cosine, and in fact any trig function we're going to study this week, is they are periodic functions. Okay, what that means is you start getting values that repeat. Okay, there's a certain amount of x values that you have to go through, and once you've gone through all those x values, you're just going to keep getting the same sequence of y values over and over. So now we looked at it a little bit earlier, and we've talked about it on the unit circle, but what are the x values you have to go through so that you go through every possible x value and then you're back to where you started? How many degrees do you have to go? Yeah, if you go through 360 degrees, you will go through every possible y value that there is, and you'll be back at the beginning. Okay, so graphically what that looks like. I'll just put this up with the notes in a second. Okay, it's like this. Okay, you get this wave pattern. Okay, and if you start out at the origin and you trace along at the peak here, that's 90. Back down again where it crosses the x-axis is 180. It hits its lowest value at 270, and then it's back at 360. Notice 360 and 0, you're back where you started. Okay, so every 360 degrees, it's like you're starting a new cycle of y values, okay, or a new period of y values. But they just keep repeating. So a lot of times what we're going to do when we sketch it is we'll just sketch one section of y values, what I just traced, and that's it. Because I know if you can sketch this one section, it's going to keep looking the same to the left and to the right. Okay, so the length of that interval over which the x values have to go before you repeat, that's called the period. Now, sine and cosine have the same period. Okay, they're both 360 degrees, or 2 pi radians. Now, that's assuming that you don't do anything to transform it. Okay, so your basic sine and cosine function both have a period of 2 pi radians. Okay, we are going to work in radians quite a bit this week. Right, now if I take, let me take the graph of sine and let me do something like this. That doesn't have a period of 360 degrees anymore, or 2 pi. It's oscillating or repeating much faster than every 360 degrees. In fact, this graph is repeating now every 120 degrees. Okay? And you might figure out how I got 120 by doing something with the 360 and the number 3. Okay? The higher I make this number, the faster it's going to repeat. Okay? That function has a period of 60 degrees. So every 60 degrees, it's going to repeat itself. Okay? So now it's repeating even faster. And we can also do the opposite. We can slow it down. So normally, whoops. So normally we get a graph that repeats every 360. This is going to be a graph that repeats every 720. So it takes longer to go through its cycle of values. Right, and we'll take a look at what that would sound like. Okay, a lot of the things I do this week, I'm going to try to tie it in with a sound. So we'll talk about what would it sound like if you played something like this that was really compressed versus something that was more stretched out. And that's not the only way you can stretch or compress it. You can also stretch and compress it vertically. And we'll hear what that sounds like as well. Okay, so those values that you have to go through before your function is going to start to repeat, that's called a period, but you can also call it the cycle. Okay, so the normal sine and cosine function have a cycle of 360 degrees, and then you're back where you started. Does anybody know where you use the term cycle to measure how fast something is oscillating, especially cycles per second? Anybody in engineering? No? How about electrical? Electrical, do you use that somewhere to measure something? Cycles per second? I'll give you a hint. It's different in the US than it is in Europe, and it's not voltage. No, not amps. Ohms? No, not resistance.
Current.
Amps measures current.
Right.
Yeah. It's the frequency of the electricity. Right? So if you have alternating current, not the kind of current in your car, that's direct current, but the kind of current in your house, alternating current has a certain frequency that it oscillates at. Okay? And it oscillates at 60 hertz. Okay? Hertz is a measure of cycles per second. That's what that is. Right? And that's an important number to maintain, especially if you're plugging in electronics that are sensitive, like computers, anything with like a high-end circuit board in it. If you're just lighting a light bulb, probably doesn't matter as much if that's exact, but like if you've got a generator and it's not the best generator, it's kind of cheap, this number might fluctuate a little bit. And what'll happen is, like if you try to run a motor that's designed to run on 60 hertz and you're running it on, say, 62 or 64, the motor's going to run hot. It's going to start to heat up more than it should because it's not quite getting the right frequency of electricity. Some devices can tolerate that fine. If you look at a lot of your transformers that you plug in for like a smartphone or electric razor, things you might travel with, a lot of them have a number on it that's, say, 50/60 hertz, meaning you can use it on either system. So Europe uses 50 hertz, we use 60 hertz. Okay, so the adapter, the transformer that you plug in, it handles the electricity coming into it fine. Europe also uses different voltage, but that's something else. All right, so Jack, were you going to say something? Nope, all right. All right, so that's a place where you do see something measured that's oscillating in cycles per second, but we're going to stick with the word period. Does anybody know the device you would use to see a picture of electricity? Same device you could use to see a picture of sound?
Something meter. Does it start with an O?
Yep, it starts with an O, but it doesn't end in meter, at least the word I'm thinking of.
Okay. On the graph first. On the oscilloscope?
Yeah, it's called an oscilloscope. Okay, and if you have, actually I have one right here. So this oscilloscope, specifically it measures sound. Okay, it's not for electrical. And as I talk, you can see a picture of my voice. Now it's not a nice wave because I'm not talking continually. I'm not talking exactly the same tone. But if I were to whistle, okay, you should see like a nice wave to it, because a whistle is a constant frequency, same pitch, same volume, nice wave. So I'll try to whistle, and hopefully you'll see a nice picture. So you can see as I tried to go higher pitch, it started to compress a little bit. If you go lower pitch, it'll start to stretch out. But you can use the same kind of device to measure electricity and check things with it. All right, so any questions on that? Okay, so that was a picture of the sound. And that device can measure the frequency. Like I was probably whistling at, maybe 1,000 or 1,500 hertz, which is 1,000 cycles per second of oscillation with sound. Relatively speaking, that's pretty low pitch, what I just whistled. Generally, humans can hear up to about 20,000 hertz. So I'm estimating I was whistling at about maybe 1,000, 1,500 hertz at the most. So we can go much higher than that. Okay, and we'll hear some sounds later in the week that are high pitch stuff and low pitch. All right, so when we want to graph a sine or a cosine function, you really need 5 basic points, okay, or what I call 5 key points. Like if you were going to do a line, you only need 2. But since sine and cosine are a little more complex, you really need 5 points. Okay, so here's a picture of one period of the sine function. It's the period that I traced over in green in that picture right there. Okay, so the 5 points you generally want to find are where the function starts and stops. That's 2, at least for that cycle, okay, for that period. We'll find the high point, the low point, and then where it crosses the x-axis. And those 5 points are all equally spaced. They're spaced every 90 degrees. Okay, we're going to do it in radians, but I wrote 90 just to kind of give you an idea. 0, 90, 180, 270, and we end at 360. And notice 0 and 360 are the same y value, and they should be, because that's where the function would start over, and then it would do another cycle. Okay, so on the x-axis, that's your angle, theta. And on the y-axis, that's the trig function of theta, whether we're graphing the sine or the cosine. Okay, this specifically is a picture of sine, not transformed at all. So if you don't transform it, what do you notice the highest and the lowest values this graph goes?
1.
Yep, 1 is the highest. And -1. Now it's super easy to transform that. Anybody have a guess what the highest and the lowest value now would be?
3.
And?
-3.
Yeah. So now this function will go as high as 3 and as low as -3. Now that's stretching it, but it's stretching it vertically. So we saw when I started to whistle and I got higher pitch, that compressed it, or if I went lower pitch, it stretched it horizontally. Does anybody have a guess what stretching or compressing a sound vertically would do? It doesn't change the pitch. What else could we change? Change what?
Volume?
Yeah, you could change volume. Okay? So if we have a wave like this, and you compare it to something like that, that's a louder sound. If you do something like this, that's a softer sound. All right. So that's stretching and compressing vertically. Versus if you compress horizontally, that's higher pitch. And if you stretch horizontally, that's a lower pitch. Okay, in this case, I only stretched one of the waves because there's a left and a right if you have 2 speakers, so you can play 2 different sounds. On my speaker, I only have 1, so both the left and the right play out of 1 speaker. Okay, so anytime that we want to graph sine or cosine, we have to know where the original function starts. Okay? I want to know these 5 points, because then if I'm going to transform it, I can figure out where it's moving. Okay? But if I don't know where the function is starting, I can't figure out where it's going to move to. Okay, so right here, you basically have a picture of sine. I just want to write these 5 values as coordinates. Okay, cosine we don't have a picture of right now, but I can graph it on the calculator and we can look at the table and copy the values from there. All right, so looking at my x-axis and looking at the first point. Nick, what's the x value of the first coordinate?
0, 0, 0.
Yeah, the x value is 0 and the y value is also 0. Yep. Let me make this a little bigger. Okay, don't worry about cosine. I'll come back to that one in a second. Okay, but the first sine point that you want is 0, 0. Okay, what's the coordinates of the second one? About Ian, what's the x value there?
The x value for the second one is pi.
That's going to be the third one.
1 over pi over 2. Sorry.
Pi over 2. And what's the y value? Should be a little, yeah, it should be a little bit, a little higher.
Okay.
Let's pretend 1 is right there.
And that's 1.
Yes, it's at 1. So pi over 2, 1. That's your second point. Priya, what about my third point? Pi, comma, 0. That's my third point. Okay, my fourth point. John, what's my fourth point?
3 pi over 2.
Yep, 3 pi over 2, comma,
Negative 1.
-1. 3 pi over 2, -1. And now the last point in this table should be back at the beginning, okay, for the y value. Okay, the x value is 2 pi, and notice the y value is 0, which is exactly what we started with. Okay, so 2 pi, 0. Okay, any questions on that table? Okay, so those are your 5 original points for sine. Anytime you want to graph sine, you always start with this table. And then we do something to either the x values, the y values, or both, okay, depending on how we're transforming it. If we're going to do anything vertical, we're going to adjust the y values. If we're going to do any kind of horizontal shifting or stretching, we're going to adjust x values, because x's are horizontal. All right, let's look at cosine. Right, so what I'm going to do is I'm going to set this up so that you see only one cycle of cosine. Okay? And they're going to have you do this a lot when we get into graphing a lot more in later sections, probably not as much this week, but they're going to say graph cosine and set it up so you only see one cycle. Well, for cosine, I know the cycle is 360 degrees. So if I start at 0 and I go to 360, that's 360 degrees. I know the highest it ever goes is 1. And the lowest is -1. So I'm going to go -2 to 2. Everything else there looks fine. So what you're about to see is one cycle of cosine. Now remember, this is a wave, so it continues on, but that's one cycle of the wave. So my x values are going to be the same. We're going to pick 5 points, equally spaced. And let's see if we can figure out the y values. So now when x is 0, how high is that point? Yeah, so for cosine, that's our first point. 0, 1. Okay, how about this point? That's at pi over 2. My y value is 0. How about pi? Yeah, right, negative 1. 3 pi over 2? 0. And 2 pi? We're back where we started for y values at 1. Okay, so sine and cosine really have the same values. It's just where you're starting. 1, 0, negative 1, 0, 1. 0, 1, 0, negative 1, 0. Same numbers. They're all shifted a little bit. Okay, so any questions on those two tables? Okay, so you really want to make sure you have those right, because if you have them wrong, every problem you graph with sine and cosine will be wrong. Okay? So when we start out for today and tomorrow, okay, we're only going to do one transformation at a time. Okay? I might give you a problem that says shift sine up 2. And that's it, just up 2. Or shift sine left 6. Okay? And that's it, I'm just going to shift it left 6. So if you're only doing one transformation at a time, then either the x column is going to change or the y column is going to change. They're not both going to change. The only way they would both change is if you do two things at the same time, like shift it right 2 and up 7. Now you're changing x's and y's at the same time. Okay, so for each individual transformation, the values in one column stay the same, and the values in the other column change. And as I said, we're going to do individual transformations today and tomorrow. On Thursday, we're going to combine them. Okay, so Thursday, I might give you a problem that says, take cosine and stretch it, shift it to the right 1 unit, and then shift it down 4. Okay, we'll combine multiple transformations together. But not till Thursday. Okay, so everything that I've given you up until this point pretty much applies to all the different kinds of transformations we're going to study. Now I'm going to specifically tell you things about a phase shift. And that's pretty much what I'm going to do for the rest of the week till Thursday. Just describe each transformation. Okay, but you guys got all the background stuff now. You got the tables, you understand what the period is, the 5 key points, all the basic stuff. Okay, so phase shift is just when you translate the graph left or right. Okay, normally we call it a horizontal shift, but for some reason when we study trig, they decide to call it a phase shift. And what's nice about trig functions, you guys should already be kind of good at them because everything is the same that you already know about other transformations. Nothing changes here. When you add or subtract a number inside the function, that shifts it left and right. What do you think is going to happen if you subtract a number? Is that going to shift it to the left? Or would that shift it to the right? Inside. Okay, the inside, that's called the argument. That's what's inside the parentheses. Nick? Yeah, if you subtract a number, that's going to shift it to the right. Okay. By how much? Well, depends what you subtract. Since we're dealing with radians, we are going to see radians come up a lot. Okay, so if you want to shift it, say, by 90 degrees, we wouldn't fill in 90 for A. We would fill in pi over 2. Okay, what about if you have x plus a number? Which way is that one going to shift? That's going to shift left. Okay, so when I teach this in trig, a lot of people get confused because they don't think of the opposite. But you guys have been doing the opposite all year. Like when we graph something like that, we should know that's a square root function shifted 2 units to the left. So we've been doing this opposite idea all year. Okay. Any questions on kind of the basics, just if you're looking at a function, how you can tell if it's going to shift left or shift right? All right. So once we know it's going to shift left or right, then we have to translate those 5 original points I gave you. Okay, I'm talking about these 2 tables right here. First of all, if you're going to shift left and right, which values are going to be affected? The x values or the y values? Yeah, it's going to be the x values. If you pick a point somewhere on that graph, okay, like pick this point, and just focus on it as I shift left, if I go like this. Okay. Whether you stretch it or compress it, or whether you just slide it, which is what we're doing a phase shift, that point isn't changing its height. All it's doing is moving left and right. So it's the x values that are going to change when you do a phase shift. Well, if it's the x values that are going to change, the y values are going to stay the same. Okay? If all you're doing is a phase shift, you are not changing the y values. Okay, so go to the original tables that I just showed you and copy down the y column, because that column's not changing. Make sure you copy the correct y column. There's 2. One for sine, one for cosine. One mistake I usually see a lot, people copy the wrong column. Okay, so make sure you copy the right column. Okay, now, to find the new x values, you're going to look at what's been added or subtracted. So in the problem we're about to do, it's that. We've subtracted pi over 2. So figure out what's been added or subtracted and do the opposite of that. Okay, so you got to remember when you do a phase shift, it's the opposite. And what are we going to do? We're going to take all the original x's in this problem, and we are going to add. We're going to do the opposite. We're going to add pi over 2. And that's going to shift all the original x values to the right, okay, by adding pi over 2. All right, so let's copy down the original table for sine, okay, before we transform it, and then we'll figure out how the values are going to change. Okay, after a while, you really get good enough that you don't need the original table. You kind of can do it in your head a little bit, but for now, let's just write the original values. Jacob, what are my original x values?
0,
Yep.
pi over 2,
Pi over 2.
5,
Yep.
3 pi over 2,
And 2 pi. Okay, and my original y's are 0, 1, 0, negative 1, 0. So I just copied that so I have it for reference. Okay, now I'm going to come up with my new table. Okay, what kind of transformation is this when you add or subtract a number inside the argument? Well, Sam? What kind of transformation is this? What's the effect of subtracting pi over 2? What does that do?
Makes it negative.
So geometrically, is it going to stretch it? Is it going to, what's going to happen?
Because it gets taller.
No, this isn't a vertical stretch. What's the one that we're studying right now? Even if you don't know the name of it, can you just tell me the direction that it moves things?
Not too
Left or right? Okay, so that's it. What's the name of that one, Ian?
horizontal shift.
Yeah, horizontal shift or a phase shift. Okay, so anytime you add or subtract a number inside parentheses, that is a phase shift. It's the only one we know so far. All right, so when we do a phase shift, Ryan, what values are not affected when you do a phase shift? Yeah, the y's stay the same. So let's copy down the y's from the original table. Okay, so our table is half done. Okay, we already have the y values. Now, we've got to do something to all the x values. Okay, I'm going to take all the original x values, 0, pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to each one of those values? I'm going to add pi over 2. Do the opposite. Okay, and we're going to write everything as an exact answer. We're not going to do 3.14 plus 1.57. Okay, we'll just leave it as an exact answer. Now, first of all, anytime you want to add fractions together, what do you have to make sure you have? Yeah, you're going to have the same denominator. Okay, so we'll put our final answers right in that box. Well, first one's pretty easy. What's 0 plus pi over 2? It's pi over 2. Pi over 2 plus pi over 2. Already have a common denominator. 2 pi over 2, which is just pi. Now the next one is pi over 1 plus pi over 2. What's my common denominator? 2. Multiply the bottom by 2. Multiply the top by 2. What's 2 pi over 2 plus 1 pi over 2? 3 pi over 2. Next one already has a common denominator. What's 3 pi over 2 plus 1 pi over 2? 4 pi over 2. And if you left everything with a denominator of 2 and didn't reduce it, let me show you the pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. How about the last one? 5 pi over 2. There's always a pattern. And the next one after that would be 6 pi over 2. 7 pi over 2, 8 pi over 2, 9 pi over 2. You don't have to graph. We're just sticking with one cycle. Okay. So there's two ways you can do it. Once you see the pattern, go by the pattern. Or if you don't see the pattern, just keep doing the arithmetic every time. Okay, find the common denominator, add it up, and then you'll see it. Okay, any questions on that? Okay, so now the last thing we got to do is graph those points. So pi over 2, we're at 0. And I'm going to label my x-axis using the values in my table. It doesn't really make sense to label it 1, 2, 3, 4, 5 because the numbers are pretty messy. So as long as you number things so they're consistent, you can number an axis any way you want. And this is consistent. 0, 90, 180, 270, 360. There's a mark every 90 degrees. Except I did it in radians. All right, so pi over 2, we're at 0. Let's see. Pi, we're at 1. 3 pi over 2, back to 0. 2 pi, we are at negative 1. And I need one more value. That's 5 pi over 2, back at 0. Okay, so here's my graph. Okay, when you graph it, do the best you can to make it look curved. No part of this graph is really sharp. It doesn't really do anything like that. It's all nice and curved. Okay, so there's our graph, and that's it. If you wanted to see where the original graph was, you don't have to in this problem. But I'll do the original in blue so you can see it. The original graph would have been about right there. Would have started here, ended there. Everything has been shifted to the right, 90 degrees, or pi over 2 radians. Any questions on that? On a test, basically all I would look for is the final graph. You wouldn't have to show me the original. All right, so let's try, I think we have 2 more of those. Let's try cosine of x plus pi. This time I'm not going to copy the original table. Okay, you've got it in your notes. You can look back at it if you need it. Okay, what kind of transformation is this? Yep, how do you know it's a phase shift? Besides, it's the only one we've studied.
It's adding, well, in this case, it's just adding to the x value.
Yeah, it's adding to the x value, very important. Completely different problem if I did that. Okay, if you add outside the parentheses, well, I'll show you that in a little bit. That's a lot easier. Adding inside, the only reason it's a little harder is because you have to deal with pi. Okay? And the hardest thing you have to do in a phase shift is really find common denominators. That's it. Okay, so John told me it's a phase shift. Connor, for a phase shift, what values stay the same? Nope, phase shift, you're going left and right. So the x's are going to change. Yeah. Yep, so the y's are going to stay the same. How about Brad? Can you tell me my y values for cosine?
1, 0, -1, 0.
Yep. In your tables, half done, okay? Because the y values aren't changing. Now we're going to take all the x values, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Sine and cosine have the same x values. And Denver, what am I going to do to each of those x values?
Subtract.
Exactly. Do the opposite. And we'll put all our answers in that table. So 3 of these are really quick to do. 0 minus pi is negative pi. What's pi minus pi? 0. What's 2 pi take away 1 pi? Just pi. And now, since everything's equally spaced, you can do the arithmetic here, or you could find out what number is halfway between 0 and negative pi, because that would keep everything equally spaced. And then what number is between 0 and pi, halfway between. Well, let's just do the arithmetic, and then on the last one, I'll just look for the pattern. What's pi over 2? Take away pi over 1. Okay, what's my common denominator? Okay, so double the bottom, double the top. What's 1 pi over 2? Take away 2 pi over 2. Over 2. Yep. Negative pi over 2. Now, does anybody see the last one? Or the fourth one, I guess? Yeah, what's halfway between 0 and pi? Pi over 2. If you don't want to try to find the pattern that way, do the arithmetic again, and you'll get the same answer. Okay. Pattern here is negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2. What would the next one be? 3 pi over 2. How about after that? Yep, 4 pi over 2, and then 5 pi over 2, 6 pi over 2, 7 pi over 2. If you reduce, you don't see the pattern as much, but I want you to reduce it. Any questions on that one? All right, so let's set up our graph. Since we're not shifting up and down, we could always do 1 to -1 for now. And everything is equally spaced. Okay, they're all 90 degrees apart. So if I make that 0, I'd have to put -pi right there. -pi over 2, pi over 2, and pi. So I'm basically showing between -180 and +180. All right, and we've got 1, 0, -1 if I'm doing it correctly, 0, back to 1. Now, this one, some people are a little bit tempted to just make a V out of it, but remember, it's part of a wave. So try to make it look curved, and remember it would keep going. That's fine. Okay, any questions on that one? As far as graph paper on the homework tonight, it's printed. It's part of the worksheet, so you'll have graph paper right on the homework. All right, and the last one I want to look at, not as much for the arithmetic, but when you graph it, the spacing is a little weird if you're not careful. Okay, so I just want to make sure we draw this one correctly. Okay, so again, it's a phase shift. My y values stay the same. So I'm half done my table. Take all my x's, which if you write them enough times, you'll memorize those x's. And what do I do to all these x's? Subtract pi over 4. This is just kind of my work off to the side. I'm not really going to be grading that. If you have a question like this on the midterm, I'm going to focus on what's in this table. All right, so the first one, 0 minus pi over 4 is pi over 4. How about common denominator between 2 and 4? 4. So double the bottom, double the top. What's 2 pi over 4? Take away 1 pi over 4. Pi over 4. The next one is pi over 1. Take away pi over 4. Same common denominator. Multiply the bottom by 4 and the top. So what's 4 pi over 4? Take away 1 pi over 4. 3 pi over 4. Now, does anybody see the pattern with the number in the numerator? It's always over 4. And there's always a pi at the end. But it's -1, 1, 3.
Odd number.
Yes. If you keep doing the arithmetic, it's odd. It's going up by odd numbers in the numerator. Everything here is still spaced 90 degrees apart. Okay? That's -45, +45, 135, 225, 315. It's just plus 90 each time, if you did it in degrees. All right, so now I want to set up the graph. Okay, I'm going from 1 to -1. I'm going to let this be 0. And let's negative pi over 4 right there. Now, let's pretend we didn't have that labeled as 0. Let me show you what some people do. So negative pi over 4, we've got 0. Is my next x value on 0 in that table? No, it skips over 0. So your next x value is not going here. Okay, that's 0. Okay? The next x value is going there, pi over 4. Okay? And pi over 4 is at 1. Now, what's the gap between negative pi over 4 and pi over 4 in terms of how many grid lines I left between them? Is there just, well, I guess that's a little tricky. If you're starting at negative pi over 4, how many grid lines do you have to go over to get to the next one? 2. So you are not putting your next value there. If you put 3 pi over 4 there, this is what's going to happen. All of a sudden, my dots don't look nicely spaced. They're kind of stretched out here, and then they're going to be squished here. So make sure you keep the gap consistent. Okay? If you have to go over 2 between dots, you're going to go over 2 between dots all the way through. So that would be 5 pi over 4, and I need one more. Okay, 7 pi over 4. Now, you didn't have to space things that way, but that's how I did it when I started, so I have to continue that spacing all the way through. Okay? So then we're at 0, negative 1, and back to 0. Okay, and that's the one that some people just get a little tripped up on the graphing because they don't space things correctly. But you'll know very quickly if you space something wrong. Your graph won't look right. Okay, so any question on the period change? I'm sorry, phase shift. That's phase shift. Okay, probably, again, one of the harder ones just because of the arithmetic, because you got to deal with pi. Okay, the last one we'll look at today is a vertical shift. And the arithmetic for a vertical shift is super easy, extremely easy. What a vertical shift is going to do is move a graph up or down. As far as a connection with sound, I can't demonstrate it. There's nothing here that lets me just take a graph and shift it up or down in terms of the sound frequency. But I can show it to you on this. Sine of x. Sine of x plus 2. So you might be looking at it and be like, well, all he did was add something. But it's where I added it. Okay? With a phase shift, you add inside the parentheses. With a vertical shift, you add outside. And that shifted it up 2 instead of left or right. Okay, so that's what a vertical shift looks like. So it has the form y equals sine or cosine of x plus or minus d. And you might be wondering, well, why did I use d? Because when we learn, there's 4 transformations altogether. Okay? You guys know 2 of them. This is the last one you would do. That's why I use the letter d. And this time, d usually is a nice number. Okay? Like plus 2, minus 3. Okay? It doesn't have a pi in it. It could, but it usually doesn't. Now, you saw what I just graphed. I graphed sine of x and sine of x plus 2. When you put plus a number, what direction did that move it?
Up.
Up. Minus a number would move it down. So this kind of transformation, don't do the opposite. In general, the rule is, when do you do the opposite? Anytime you're doing horizontal stuff, do the opposite. Anytime you're doing vertical stuff, don't. And that's the same rule we've been doing all year. Okay, so add moves it up. Minus would shift it down. So if we're going to shift things up and down, what column or what values are affected when you shift up and down? X's or Y's? Y's, right? If you're shifting up and down. that means the x's are going to stay the same. And that's, why is that a real good thing? Whenever you can keep the x column the same. Because they're all in radians, right? Those values in the x column are hard to work with. Now we're not going to have to change them. We're going to get to change the easy values, the 1s and the 0s. Okay, there's 2 transformations where you have to change the hard values, and there's 2 transformations where you have to work with the easier values. Okay, so for a vertical shift, copy down your x's. They're not going to change. And all you have to do to find the new y values is add or subtract whatever d was, okay, whatever that value was, to all the original y values. Okay, so if I had a problem like this, cosine x plus 2, I'm going to do a plus 2 to all the y values. Don't do the opposite. I don't know any other way to say that, but on the test, somebody always does the opposite for this function. Okay, just on your reference sheet or in your notes, put, don't do the opposite. Opposite is for a phase shift. Okay, so I'm going to copy down my x's because they stay the same, and I'm not going to have to do anything with them. So Denver, can you remind me what my x's are for cosine or sine? They're the same.
To 2 pi.
Yep, all the way to 2 pi.
0, 5 by 2, 3 pi, 3 pi over 2.
So those are my x's. And John, what are my y values for cosine, the originals?
1, 0, and 1, 0, 1.
1, 0, negative 1, 0, 1. And what am I going to do to all these y values? Add 2. And that's it. Now just fill in your new y values. Okay, so Fred, can you give me all my new y values?
3,
Yep.
2, 1, 2, 3.
That's it. Okay, so transformation in terms of arithmetic, this one's a lot easier. Now when I label my x-axis and y-axis, I might have to adjust a little bit. Okay, I got to go up to 3. And I'm going to label this 0, pi over 2, pi, 3 pi over 2, 2 pi. What's nice when you do a vertical shift, these values never change. Every time. Always the same. Okay, so we're at 0, 3, 2, 1, 2, 3. So that's my cosine function shifted up 2 units. And what sometimes I do is I kind of draw how it would look just to kind of get the pattern for it. Then it would continue on. Okay, so any questions on that? Okay, so that's a shift up 2. And the last one we'll do is a shift of sine, except now we'll shift it the other way. Okay, Ethan, how do you know this is going to shift up and down and it's not shifting left and right? Okay, but you could have subtraction and still have it be a shift left or right. Yeah. So how do we know that that's not shifting left and right? Because it's on the, yeah, what were you going to say, Lauren?
Because it's not in parentheses.
Yeah, it's not in parentheses. This is a totally different problem now. Now it is shifting left or right. Specifically, that would be right 3 units. Right? If you don't put it in parentheses, it's always shifting up or down. Now, you can put parentheses like this. That doesn't change the problem. You can also put parentheses like this if you really want to. That doesn't change the problem either. It's when the x and the 3 are together in the parentheses. All right, so Bria, can you tell me what my x values are for sine?
0, 5, 2, pi, 3 pi, and 2 pi.
All right. And my y values. Hannah, can you tell me what my original y values are for sine?
0,
Yep.
1,
Yep.
0, -1,
And 0. All right. And now, how about Curtis? What am I going to do to all those y values?
Subtract 3 from 1.
Yep. Subtract 3. And can you tell me what you get when you do that for y values?
-3, -2, -3, -4, and -2.
Okay. And when you graph it, you kind of know if you did something wrong because your graph, it doesn't look right. Chances are if the graph looks everything nicely spaced, then it's probably right. All right, so I've got 0. Do I have to go below -3? Yep. -4. And I'm going to put my x values at the top this time. You can put them at the bottom if you want, but okay. And in terms of grading, the way I usually grade a question like this is I give you 1 point for each x and y value you get right on a test or the midterm. So you'd get 10 points if you get the table right, and then the graph itself is usually worth just a point or 2. Because the graph is easy once you get the table. All right, so let's graph it. So we got 0, -3, pi over 2, -2, pi, -3, 3 pi over 2, -4, and 2 pi, -3. Those points look nice and even, so we should be good. So that's your sine function shifted down 3 units. Okay, so any questions on that? Okay, so today we did all the, what we call rigid motion transformations. You just take what you have and you shift it left and right or up and down. Tomorrow we'll do the transformations that stretch up and down. Okay, and I'll play that so you can hear what that would sound like. And a little more interesting, when you stretch it left and right, and I'll play that and we can see what it sounds like. If we have time, I'll try to do the cell phone thing. I don't think I've done that in here, where I can basically control a cell phone just by playing the right frequency sounds without touching. Have I done that in here? No? All right, so if we have time, we'll take a look at that. There's a couple of things we can look at with music too, if we have time. Okay, so the homework tonight is these 7 problems. They are on a worksheet, so mainly this is just for people watching the video, but those are the 7 problems you can do, but I'll pass them out on a worksheet for you. And again, no test this week because of the snow day on Monday.